Okay, today we'll have an introduction of MATLAB as a programming language. This is part 2. Okay. The first part we will go through a whole bunch of MATLAB functions. This includes mathematics functions, vector functions, and many other different kinds of useful functions. We start with basic math functions. Okay. These are functions applied to numbers, and if you have a vector or an array, these functions are applied to each element separately and give you an array of the same size and generally the same case. For example, round, ceiling, and floor are for converting floating-point values to integers. Okay. Yeah. And ABS, of course, is absolute value. Okay. Absolute value for real numbers normally is just, is absolute value. If it's for a complex number, then you get the magnitude of that complex number. Right. We haven't introduced the complex numbers. I'll give you an example here, like this. Okay, that will be a complex number. Yeah. So you can see that I have the real part and the imaginary part. Okay. This is the square root of 5, which is the magnitude of a here. And then we have the exponential and the logarithmic function. Okay, this is natural logarithm. Okay, and then you also have the base 2 and base 10 logs. And then the very standard triangular functions, sine, cosine, tangent. And these are the arcsine, arccosine, and arctangent. The a in front represent that they are inverse functions. The ATAN2 is somehow different from ATAN in terms that it takes two inputs with the y and x separately. The reason is that the arctangent function gives you range of just between minus and plus 90 degrees. And the ATAN2, by taking in both y and x, it will be able to give you the degree output over the whole 360 degrees. These functions in their best standard form like this, they work all with radians. The angles are in units of radians. If you want to work with degrees, then you should go with a version that has a letter d attached to the function name, like sine d, like this. That means it's the sine function in the degree form. Okay. Yeah, like this is the sine of 1 radian. This is the sine of 1 degree. Yeah, so this applies to all these triangular functions. And of course, for the very standard constant pi, it's reserved as a constant. That's what it is. So for the previous slides, those are functions applied to individual numbers. Here we're talking about functions applied to vectors, and also they can be extended to arrays. Basically, let's first consider vector functions. There's functions sum and mean. Actually, for sum we have used in the previous lab task, and for mean it's just the average. For simplicity, let's define a vector here That's vector 1, 4, 5. Okay, that's the sum. That's the mean. Okay. Or you can have the median, which is a number in the middle. And in this case, they are the same. Okay. If I take this as square of b, okay, this is the mean, this is the median. Oh, sorry, I should say the b2, mean, and median. Median will be 9 here. Okay. Cumulative sum and cumulative product will give you a vector, okay, instead of just the total sum or the total product. We can compute the total product. I didn't list it on the slides, but it's similar like this. That's the product. Okay. B is 1 to 5, so product is the same as b factor. Cumulative sum of b, you can see, yeah, each number is the sum of the first first few elements of the original vector. Okay, so that's the first 2 elements, first 3 elements, first 4 elements, etc. Okay, similar for cumulative product. So these are straightforward when we only apply the functions to vectors. Okay. The vectors can be row vectors or column vectors. Yeah. As long as it's a vector, that means as long as it has only one non-singleton dimension, then these functions are very straightforward. Now, a little different is when you apply it to multi-dimensional arrays. For example, let's create one array using a random number generator. Okay. So those are some random numbers. For simplicity, I'm going to convert it to something like this, make it easier to look at. Yeah, you can see I use the function run there. This is how we can get random numbers in any desired range. Like in this case, the random numbers are integers between 0 and 10. Okay. Now, if I apply the function sum here, you get a vector from the 2-dimensional array. Basically, sum is a vector function, so it will apply to the first non-singleton dimension. Here is the dimension along the columns. So it will compute for each vector along this dimension. Okay, so this is what you get. The 24 is the sum of A97, and 19 is the sum of A74. Okay. So if you know the first non-singleton dimension, then you can just use this. Otherwise, you can specify the dimension index. Okay. So what we just had is the first dimension. And you can also do it with the second dimension. Okay, so for this is summed along each row, so that's 23 is A plus A plus 7. Okay, like that. Yeah. This mechanism applies to all the other vector functions. Okay, like you can also do a cumulative sum. Okay, let's see it. You can see how it works. Okay, a cumulative sum is done for each row separately. Now, what about if we want to just sum the whole array together? Okay, back to C. The easy way is just to convert it to a vector. Okay, this is how we convert an array, any dimensions, to a single column vector. I'll let you see it first. This is what it looks like. That's a single column vector. So, no matter what the original shape is, you can always do this. That's the sum of the whole array. Yeah. Of course, if you are doing the cumulative sum or cumulative product, yeah, you need to keep in mind the actual ordering in the memory of the array elements. Okay. Now, we're getting into two other functions that can work as vector or array functions, but they are a little more complicated. That's min and max. To reduce the duplicates, I will get back to the random number generator, and because I don't want any duplicate, I'm working with min or max so that we don't get any ambiguity. Okay. Let's say that we do min of C. You can see what happens is the minimum along each vector. Okay. But for the dimension, we cannot just, if we want to do it minimum, take the minimum along each row, if we just do this, well, okay, it actually just take a element-wise minimum with that scalar 2. Yeah, so from here you know that when you have just two inputs, okay, those two inputs are to be compared, so it becomes taking the minimum between two inputs. So then how do I specify dimension if I just have one input? So this is how you do. You place an empty array as the second input and specify the dimension as the third input. Okay. Later on, when we talk about functions, we're going to introduce how to code with a variable number of inputs and outputs in MATLAB. Okay. This is one of the very representative example within its built-in functions. Okay. So that's the minimum along the rows. So 10, 19, and 3. The same thing applies to max. So the next thing is, let's play with the sorting function. Again, if you are sorting along vector, then it's easy. Generally, it's an ascending direction. For array, I can sort along any dimension. Like in this case, it's sorted along each column. Okay, so from small to large. If I want to change the dimension, this is what I can do. Okay, I can specify the direction. This is from large to small. Okay, see, that's the horizontal direction. Now I want to introduce one thing about sort. Actually, similar things can be used with min and max, but I'm using sort to illustrate retrieving the index. Okay, so I'll give you a vector that's actually a little longer. Not very long. Yeah, I'm just using a vector length 5. Okay. Now, if I sort it, it's naturally from small to large. Okay. If I want to retrieve the index, I can specify two outputs for this function. The first output will be the regular sorted result. The second output will be the index. Those are the index of the sorted elements in the original, like this. Can you tell? 28 is the fifth element here. 45 is the first element in the original vector. That's what they are. So basically you can get to the original vector by doing this. You can get the sorted result by doing this is the same as the sorted result. Okay. Having the index is very useful when you are sorting something that's, for example, the data items are actually quite large, so you don't want to sort them directly, but you may sort about one of the attributes or by some ID or something, just some numbers that you can sort out. Then after sorting, you retrieve the indices. That way will allow you to access the original data items in the sorted order. Okay. So the index is actually very useful. Finally, for this slide, we're introducing the logical vector functions any and all. Okay. Any is just logical OR over all the elements along a vector. For this, I have to create a logical vector. Okay, that's a logical vector. The functions any and all, when applied to a logical vector, will just give you a logical value. So any just is an OR. As long as any one of it is true, the result is true. And for all, that's AND. So it requires everyone to be true for the output to be true. Of course, this can be applied to arrays as well, with specified dimensions. They all follow very similar formats. After talking about those logical operators, we're going to introduce another thing that's very important in array indexing. That's logical indexing. Logical indexing means to specify or to extract, to identify some of the elements based on some logical positions. Okay. So let's get back to one of our original random number array. Okay. Let's put a condition. Okay, like C is larger than 50. This is logical condition that will be applied element-wise. So you get a logical array with the value depending on whether each element satisfies this condition. So that's false, 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 that's true, like this. Okay. Wherever a logical array is displayed, it's displayed with numbers with 0 representing false and non-zero representing true. So that's logical indexing, and we can actually save it to one of the variables. Okay. Now, if I do this, I'm applying the logical conditions to the original array, and it will extract part of the array that satisfies these conditions. In this case, there are 5 elements. Okay. Since you no longer have the array shape, okay, because right now you have only 5 elements from that original 3x4 array. Okay. So basically, this will be just a basic column vector, okay, which are the 5 elements in their original order in the memory. So that's 82, 69, 95, 77, and 80. And then we can do the assignments with this. For example, get back to C. I want to replace those elements with, for example, 100. Let's see what happens. Okay. So the assignment only happens where F is true. In another example, you know I have 5 elements, okay, and I assign 5 different values to it, okay, so it will follow that order. 101, 102, 103, 104, and 105. Okay. I can do many different things. Okay, it's already this big, so those 5 elements will be added by 100. So logical indexing allows you to do many array operations based on the same logical conditions, and it's very flexible. Allow you to write very compact codes instead of using loops and some if else, that kind of operations. If you're writing in C, that's what you have to do. Okay. Have a loop going through all the elements and then check the conditions and do what you want to do in that if-else blocks. And in MATLAB, this is how you do it. Talking about logical conditions for array elements, we also introduce this thing, find. Find is a very useful function. Okay, I will recreate an original C from random number generators. Okay. And this is our F. I should do the F because the array is not different. So this is the condition. Okay, the new F correspond to the new current array C. Okay. Now, find is the operation that extracts the indices of the non-zero or the true elements from a logical array, the true elements. So this is what you get. That's 1, 2, okay, 3, 4, 5, 6. Okay. Linear 6, 7, 8, 9, 10, 11, 12. So you get the array here. Okay. You find those elements. That's if you just do not specify any output or just specify one output like this. Okay. You can specify 2 outputs. For either reading, I will combine the R and C, so that makes it easier. And let's look at C itself. Oh, too bad. I changed the content of that variable. Okay, now let's just use F. Okay, and So the first column is row, and the second column is column. Okay, row and column. So you can actually get the subscripts of those true elements. So that's 1 1, that's 2 1, row being 2, column being 1. That's 1 2 3, 3 2. Okay, so that's row to second column like that. Okay. For the matrix operations, most of these are going to be a little fast, okay, because those just come from the linear algebra. Okay. Dot, that's inner product between vectors. Cross, that's the cross product or outer product of two vectors, and they apply to vectors of the same length. Okay. If you have square matrices, you can use the function diagonal to get the diagonal elements. The trace, of course, is the sum of the diagonal elements. Transpose, right? MATLAB has a more generalized transpose function, but most commonly, when we just want to do simple two-dimensional array transpose, we use, that's a single chord. Too small if you can already tell. That's a single chord. Okay. So I will create another array anyway. That's a transpose. Okay. And if you add a period before that single chord, that's a transpose as well. They're different only when you are working with complex numbers. Okay. Just a single chord will give you complex conjugate transpose. And a period with a single chord, that's a regular transpose. Okay. So you don't see difference for real numbers. Okay. This should be straightforward. Flip, left, right, flip, up, down. Okay, for two-dimensional arrays. Okay, and those matrix operations. Okay. Using a single multiplication, between two arrays, that's matrix multiplication. And for this, that's matrix power. So to do element-wise multiplication and element-wise power and all those things, you need to use the dot, or the dot plus the operator. Okay, like we talked about last time. This backslash operator will just introduce it in the next slide. And there are also a few things that's a norm of vectors. The inverse of matrix, of course, that's for square matrix, if it's inversible, and that gives you the eigenvalue and eigenvector. So useful, very convenient if you want to do some linear algebra works. Now, we will particularly introduce this backslash or left division operator. Okay. It's very useful for solving a set of linear equations in the form. Okay. Here, A is a square matrix, Z and Y are the column vectors, and so that's a set. If Z and Y, if Z contains the non-variables and nouns, then this is a set of linear equations, and this can be solved by this simple statement. Okay. And if you have more points or more equations than your nouns, that's when A is not square, but A actually has more rows than columns. Then you get to the mean square error approximation of linear regression, okay, like fitting a line. But of course, you can extend this beyond lines, okay, because actually, even if the equations are not linear, that you have squares, like in polynomials, you can still solve for the coefficients. We're going to illustrate this a little bit with a simple equation like this. So we start with point of A of, let's say A is 2, okay, B is 3. Let's press the output so we don't see too many things. X is 0 to 5, so get 5 points. Okay, Y is A times X plus B. Let's see our X and Y. That's X, that's Y. Okay. Now to solve the equation, let's follow what's on the slide. This A will be, that will be X transpose, and that will be 1 of this of X and Y. That will be A. And the unknowns we solve by A minus Y will be, I'll have to take the transpose here. Okay. Yeah, because over here that's the column vector. Okay. So we solve A and B. That's the output A and B here. Okay. Now, back to the original, if we have a little bit of noise, okay, and I'm going to scale the noise a little bit to between some minus 0.1 to 0.1. Okay. I'm not going to explain this too much, so later you can just look at this to know what happens. Okay. Yeah. So let's look at X and Y again. Compared to the original, you can see there's a little bit of noise in there. Now, let's do this. Okay, yeah, it's still pretty close to 2 and 3. A little bit different because it's linear regression. Yeah, this is real convenient. Next, some extra topics. Yeah, vector sets. MATLAB has set functions. Okay. The thing about sets is that there will be nothing duplicate in the sets. Okay. Within the set, a set is internally is a vector where every element is different. Okay, that's a set. So consider those are the sets. You can do set operations like the intersection, union, set difference, and set XOR, which is will return the elements that's in one set in one of the two sets, but not in both. Okay. I'll give you a couple examples. Okay, like those can be considered two sets, and I'll just give you like this. Both. This will return indices, but I'll skip those for now. Similar to sort, the indices tell you the places in the original vectors, okay, or the original sets, yeah, their positions. And with two inputs, you actually get two elements, two set of elements, or the indices, two set of indices. A relative function is unique. Unique will remove any duplicate, okay, and give you a vector that have no duplicates. Okay. So those are the introduction of some of the useful functions, the class of functions. Okay. Then we'll get back to something about actual programming, writing programs. Okay. We will start with just scripts. Scripts are just collection of statements, and yeah, you have tried that in your last lab task. You can save the statements collections in M file so they can be executed later. Okay. Scripts have global scope. That means they share the same set of variables with your workspace, and you can use the editor to edit your script. Okay. The comments are lines that start with the that percent sign. Okay. You can have block comments. That's a multi-line comments. For block comments, you need the first and the last lines to be those two. Okay, you have to large brackets that were used to the beginning of the first line. Okay, and that's the last line. With those, the MATLAB will know you have block comments, so you don't need to type the percent sign before each line. Okay. The last, the 3 periods, this is, I know it has a name in English, I forgot. Okay. And for that, if you, in the program, if you have a line that's really too long, you can use this for line continuation. Finally, to write programs, want to introduce the standard, what I call the program control or program flow control structures in MATLAB. And basically, they are very similar to other languages like C. Basically, there are 4 of them that we'll talk about. 2 are the conditional branching. That's the if-else type and switch case type. Okay. And there are 2 loops. Okay. The while loop and the for loops. So we're going to go through them one by one. For program control, that's for the if-else. Okay. That's very standard, just put them in separate lines. If, and you can have multiple else if. After each, that should be a standard logical expression. Okay. You have to know that if that happens to be a vector, a logical vector, then it will be n. Okay, because the condition has to be met on a single logical value. And if those happen to be numerical values, then they are treated as true if they are not zero, or false if they are zeros. The use is very much the same in any standard programming language, so I'm not going to talk too much. Okay. The switch case is just a good way to list multiple branchings together. Yeah. So if you know switch case in C, then these are also quite similar, yeah, with a little bit of wrinkles. Again, the switch conditions is something to be compared with all the different cases, and the cases have the statements. The difference from C is that in C you need to break every block, the statements after each case, otherwise it will continue the computation following the first metric case. Okay. But in MATLAB, each case is independent. So once the switch expression gets you into a case, in there it will jump away. Okay, will just break from there without you needing to specify a break. Okay. And for finally, there's an otherwise. Okay. Otherwise means when none of the cases are matching conditions, then it will execute the statements and the otherwise. This part is optional. You can just skip it. If you don't have an otherwise section within your switch block, then if there's no matching case, then it will just skip the whole thing. Another thing that's different from C is that the matching conditions or the case expression can have actually multiple values like this. So you can place two conditions, two matches into one case block. So if this is compared to some variable in switch expression, then when it's either 1 or either 2, that case will be executed. This kind of expression we haven't used so far. Specifically, that's called the cell array in MATLAB. But for that part, we're going to get to that later on, not here. So for now, just remember that each case block can have multiple matches. And one thing nice about MATLAB is that the switch and case expressions can be strings. So if you have this as a string expression, a string variable, and all those case expressions are also strings, the string comparisons can be directly processed. Then finally, we talk about loops. The while loop is very standard. While there's a logical expression here, if it's true, you execute the statements and it back there. Very standard while loop. The for loop is a little more interesting. For loop requires a control variable, or sometimes we use that as a counter. So the variable will be a sequence of values. The control, generally, if we just want to do something like count from 1 to 5, like this, I'll print that control variable. Because I'm using the command window, so I try to squeeze everything into a single line. And the II, let me do this to save space. So it will print the control variable here. One thing interesting is that for the control variable, you can do something like this. So this is not like a counter, but it's just iterates over a vector or a number of elements, like this. And this is what happens if we have some array, two-dimensional array. Actually, this loop only goes out twice. This is what that array looks like. So the first time it works on the first column, the second time it works on the second column. This sometimes can be confusion. That's how it works. It loops over the first non-singleton dimension. Sometimes this is useful, but you have to be careful about it. So for normal use, just make your control variable, the values of your control variable into a normal vector, row vector. Okay. Yeah, that's the easiest way to avoid confusion. Another thing is that in C, it's very common to we use the I and then J as the name of the control variable. That's almost like a convention. The problems in MATLAB is that I and J has other meanings. That's the square root of -1. The same for J. Yeah. So, yeah, you can still specify, but that way you will override the reserved variable names I and J. So, generally, to avoid problems, don't use I and J as your variable names. Okay. Similar thing for that. The other reserved variable name, that's pi, pi. Okay. I can set pi to a different value, but that's a problem. Okay. If I set this, then it becomes 2. So, at the end of the flow control, there are two things. Those two commands are the same as in like C or Python or those common languages. Okay. When break is within a loop, it terminates the current loop. Okay. If you have nested loops, then the innermost loop that contains that command is terminated. Okay. For continue, you just terminate the current iteration, but it will continue with that loop. Just start with the next iteration. For the last part about today's discussion of all the operations, I want to emphasize the skill or technique of vectorization, which is that if you can do something with vector functions or array functions, then don't use loop. Okay. This is because the nature of language like MATLAB, and also actually similarly for Python. Okay. Because they are basically interpreter languages. That actually is a lot of cost. Yeah, expensive to process the loops. Okay. In C, it's not expensive because the basic loops in C works almost like it's in assembly language. Yeah, but not the case in MATLAB. So for the operations, like a lot of the standard array and vector operations, they are already implemented and compiled as C routines that can be called from MATLAB. Yeah. You might not notice that, but a lot of those things, like if you're running sum, okay, yeah, internally it's written in C, but then it's wrapped as a MATLAB function for you to call. So with those optimizations in C, that's a lot faster. Whenever you can use those instead of using loops, yeah, do that. Even if this appears less efficient on the surface, that means if you think about working in C, then if you code it yourself instead of using some vector functions, yeah, you will think that you will save some computation because, for example, some elements do not have to be processed. Okay. Yeah. But if you actually write a loop in MATLAB and try to avoid those extra work, yeah, it's slower than just let the vectorized version do everything in C. Okay. So for comparison, here I'm just giving you some examples of two equivalent two equivalent operations. Okay. There are three things copied here, so I'm going to repeat the process. Okay. So for this, I create a large array of 200 million elements. The first way is to use loop to compute the element-wise square. Okay, element-wise square of the array, and it takes a while. If I do this vectorized version, it's faster. Yeah. Maybe you don't see a lot of difference in time here, so let's make the array bigger. You can see the memory allocation itself takes some time as well. And let's put out some timing. Okay. In some future lectures, I'm going to tell you about this use of tick and top. But that basically is just a straightforward way to give approximate execution time. Now I should put the 5 here. Okay, so that's about 2 seconds. And for this version, that's the vectorized version. Yeah, that's about 1/4 of the time used. Okay. Although those two actually do exactly the same thing, but one does it in C, the other does it in MATLAB. Okay. Actually, for MATLAB, it's not all the straightforward interpreter. It already has some internal optimization. Yeah, to create, like if you have a loop, it already creates a program code. So each time it processes the loop, it's not as expensive as real interpreter would do. Okay, but it's still much slower than if you have something that maybe you don't know, but internally this is implemented in C, in the element product, array product, like that. So keep this in mind, yeah, whenever you work with MATLAB. That's all for today's course here. We'll see you next Tuesday.